Hello everyone, Alex is here. I came with a new video, and this video is going to be on one of my favorite topics. In this video, I will talk about how to do Monte Carlo simulation using Excel. Quick story here, I first learned about Monte Carlo 2 years ago in that class, 640, and I have used it since then in other classes, at my work, and even in my personal life. I'll show you some of these examples here today at the end of this video and how I used Monte Carlo to do work time analysis study. I find Monte Carlo to be an extremely powerful tool, and Excel has all the basics to make you utilize it without too much effort. Even though there are two main flaws with Excel that I hate, and I'm going to mention those in that video. They are both related to Weibull distribution, unfortunately, which is the most important distributions that we use in the reliability domain. I remember when I first learned about Monte Carlo in lecture 7, it was a new subject to me, and it took me a bit of time to understand how to apply it in Excel. So I hope this video gets you there quicker so you can enjoy the next series of lectures that the professor has for you. We'll start first by taking a quick glance at one of our lecture slides. And as I mentioned before, those videos are just to teach you how to demonstrate what you learn in the lecture. So I'm not going to explain the whole concept here. We're just going to brush off on the first graph, which is the CDF, cumulative distribution function, which is the cumulative probability of failure as a function of time for any distribution. Here, it happened to be a Weibull distribution. Then in the second graph here, we're taking the inverse of that, which we call this quantile function. This is your P10, your B50. To get that, it's really easy. You're just taking the argument of that function with respect to time. So you're basically separating the time. We have a whole new video about that. I believe it was the first video for this semester. So I'm just making an argument here to get t by itself and get the inverse function. Then, in that third graph here, I'm using the uniform distribution as my roulette wheel. Monte Carlo is a gambling game. You spin the wheel and the ball gets in a number, and this number is a winner. So instead of spinning the wheel, I'm using a uniform distribution that can give me any value between 0 and 1. And if you notice here, the 0 and 1 are lined up with the 0 and 1 of the inverse distribution function. So basically what I'm doing here, I am getting a random value from that uniform distribution. I'm using this random value as my probability, and then I'm going to get the corresponding failure time for that probability. I take more random value, I get the corresponding failure time, and I keep repeating that one after another. And that's how I'm doing a Monte Carlo simulation. We will start here by learning how to generate random data. We will do that in Minitab, and we will also do that in Excel. However, I want to make a really important distinguish here. When we get data from Minitab, it will be a random sampling from a given distribution, i.e., it will be a failure time randomly picked from a given distribution that we will tell Minitab. But when we get data from Excel, it will be just a random number between 0 and 1, which we will consider that number to be the probability, because as we all know, the probability is always between 0 and 1. Then we will use Excel formulas to inverse that probability number into the sampled failure time. If that doesn't make sense to you now, that's okay. Just remember, Minitab gives you random sampling of failure, and Excel is just giving you a random number that we will consider to be the probability. I will repeat that distinguish at the end of the video, but with that being said, let's start with a Minitab example where we will obtain random sampling data from a given distribution. In order to do that, we will first assign the column where the random sampling will go. And then we will go to Calc, Random Data, and we're going to choose a distribution we wish. We have normal. We also have Weibull. Remember that. We have Weibull here because we will need that later in the video. So let's just go with normal. And I'm going to say I would like 100 sample, maybe 1000 sample of a normal distribution. I already chosen that my mean will be 5 and standard deviation of 2. And I'm going to assign where I want this data, and I'll hit OK. And I'm getting random sample from a normal distribution. As I'm scrolling down, you should see a lot of 5s, a lot of 4s, and a lot of 6. Why? Because that is the mean of that distribution, and all the random data should hover around that mean. And we'll see that more in Excel, but you see a lot of 5s, a lot of 4s, and you should see a lot of 6 as well. All right, that was for Minitab. Now let's go to Excel and see how could we do that. In Excel, you will see that we don't get a random sampling directly. Instead, we will get a random data, aka random number between 0 and 1. And then we will transform that into random sampling from a given distribution. To get the random number in Excel, we're going to use a formula equal random, R-A-N-D, and you're going to leave the parentheses empty. When you leave it empty, that will give you a random value between 0 and 1. So here we go. I can expand that to get more values. Let's get 25 altogether, for example. And you notice here that every time I make a change or I press a button in Excel, everything changed. That's because I'm asking Excel for a random value. And every time I make a change, Excel recalculate all the formulas. If any of you does logic diagram or deal with PLC, this is the same concept. Excel is constantly scanning every formula every time it senses a change. If that bothers you and you would like everything to stay the same until you finish your spreadsheet, then calculate the data, you can go to Formulas, Calculation Options, and change it to Manual. Now, you make changes, nothing changed. If you would like to ask Excel to run every formula, you press F9 in your keyboard, and everything changed. F9, another F9, another F9. However, I like everything to be dynamic, so I'll put it back to automatic. And again, I want to go back real quick to the lecture slide and take a screenshot of that to tell you what we're doing here. Let's do that. Here, what I did is I used Excel to give me random data, and I use this random data from the uniform distribution, which is between 0 and 1. I consider it to be the probability, and then I'm going to go to inverse that probability to get the corresponding time. In order to do that in Excel, we're going to make a live example together. Let's arrange our workspace to be for a normal distribution. I will use mean 5 and standard deviation 2. And I'm going to collect some random data. Again, we all learn how to do that. Random, parentheses, and I'm just going to go with 25. For each of these random data, I am going to go ahead and ask Excel to give me the inverse of this probability, which is the corresponding failure time. So I get this data, I went up, and I'm trying to get that corresponding time. So that'll be my failure time, and it's going to be norm inverse, the probabilities that I have, the mean of the distribution, and standard deviation of the distribution. And that should give me the corresponding time of failure for that probability. And I can expand it. Obviously, if you're really attentive, you can see that when your probability is 0.5, you should have time of 5. Because when you have a probability of 0.5, you are in the middle of that normal distribution, right at the mean, and the mean of that distribution is 5. So let's hit refresh until we find our target here. Here we go. 0.5055 corresponds to time of close to 5. If you would like to make another verification, if you took that failure time and inversed it one more time, I'm going to say true, that should give me bags of probabilities that I have. So that tells me I am correct. Again, we don't need that anymore. All right, let's do some more visualization for Monte Carlo. First, if I to ask you what is the average of all these sample time, it will be 5, because that's the average of that distribution, or the mean of that normal distribution. So let's say this is going to be the mean, and that's going to be my standard deviation. And I know they are 5 and 2, but we will look at the sample times that we obtained. So I'm going to say average of these times and standard deviation of these times as well. And you should see that this should hover around 5, this should hover around 2. It would probably be a really small probability of you seeing 5 and 2 at the same time. So let's do that. 4.6 and 1.9, 5.3 and 1.66. As a matter of fact, this is for sample of 25. In order to do some visualization, I want to show you how Monte Carlo is powerful as it gets bigger. I'm going to start the 5 column here. I'm saying given mean, which is the mean that I already have for that distribution, and given standard deviation, and calculated mean, and calculated standard deviation. The given mean is always going to be 5. We know that. And the given standard deviation will be always 2. We also know that. The calculated mean and the calculated standard deviation, those will change based in here. And in order to do that, I want to show you how it shows on a graph. Let's copy these two data here. All right, I hope you are following what I was doing. What I was doing here is I'm showing you my mean from the distribution and the standard deviation from the distribution, and the blue dot will be the standard deviation and the mean from one of my samples. So let's do another one. F9. Let's copy that. I'm getting different means and different standard deviation, but they're all around the mean of the distribution and the standard deviation of that distribution. Keep sampling more. And remember, those are not really far off. I have my scale here from between 4 and 6, and here from 1 to 3. If I change that scale to be from 0 to 10, you will see how close I am, right? But again, I just want to focus on 4 to 6. Just keep taking more data. All right, you got it. You're always hovering around the mean and the standard deviation. Now I'm going to take a screenshot of that for my reference. I put it right here, and we're going to increase the number of samples from 25 to 2,500. So let's do that. All right, 24 is enough. I'm going to expand my failure time inverse. Now I'm going to take my average up to Now I increase my sample size from 25 to 2,400. Now let's see the effect of that. Look at my mean and standard deviation. they are much, much closer to the actual mean of the distribution and actual standard deviation of the distribution. Wow, you see the powerful of it now. You see, comparing to before, I'm using the same scale here, 4 and 6 and 1 and 3, but all my mean and standard deviation are almost identical to the distribution mean and distribution standard deviation. This is one of the most powerful things in Monte Carlo simulation. Some people go even 100,000. Here I'm using one normal distribution, so everything is easy for me. But you will see at the end of this video, you can do more complex things, and that's when the number of iteration will make a difference. If you go from 1,000 to 10,000 to 100,000, it changes everything for you, and the more, the better when it comes to Monte Carlo. All right, now let's change all of that to a Weibull distribution. We're going to keep everything here similar, but I'm going to delete that. This is going to be a Weibull distribution now. And I'm going to have an alpha of 5 and beta of 2. We'll leave those. Now, if I decided to use the same random data to get the corresponding time of failure at a Weibull distribution, I would expect to do the same, which is equal Weibull inverse, and I don't see Weibull inverse. Okay, this is your first flaw in Excel. Unfortunately, Excel does not give you Weibull inverse as a formula. I don't understand why. It is really easy. So if you would like to get random sampling time for a Weibull distribution, your easiest route is to go to Minitab and go to Calc, Random Data, Weibull, let's say 1,000, shape parameter of 2 and scale parameter of 5, no threshold, and I wanted to go to that column and take this data, copy it, and go to Excel and proceed. This is probably the easiest route. However, when I took this class, I did not want to settle to that idea that Excel cannot inverse Weibull. So what I did is I utilized something we all learned from that class, and I made an argument for the CDF. Let's take a look at that. I know this is the CDF of a Weibull distribution. I made an argument with respect to t, and I came up with the equations that will give me the time, which is alpha multiplied by negative the natural log 1 minus the CDF, or the probability, power 1 over beta. Then I used this formula, and I went back to Excel, and I start to use it. So my formula say minus the alpha multiplied by negative ln 1 minus probability of failure, and remember that your power goes outside, 1 over beta, and I get failure time. And that's how I came up with a quick equation that can help me in Excel to get the inverse of a Weibull distribution. Someone can say, I'm questioning that approach. I don't think this is true. All right, the only way to do that is a quick verification. And just like we did the verification as a normal distribution, we can do it in the Weibull here. What I'm saying here is I was able to obtain the corresponding time of a probability in a Weibull distribution using this formula. So technically speaking, if you took the Weibull distribution of that time, you should be able to obtain this probability value. And we can verify that easily. But this is going to take us to the second flaw in Excel. Let's go to the help real quick and see what is the definition of a Weibull distribution in Excel. If you look closely here, Excel defining the Weibull distribution, which we already have here. Let's take a quick screenshot of that. Like everything to be in front of you. This is my CDF that we use in our class and probably most of the practitioner use. But look, Excel here is reversing the alpha and the beta. Instead of e to the power negative x over alpha power beta, Excel is doing x over beta power alpha. So basically, Excel have alpha and beta reversed. And I want to make sure this point is clear. Now you know why. If you took 602, you probably know. Delete that. Let's go back and let's do the verification. We'll do whiteboard, and this is my time. Alpha, remember, alpha will be beta. Fortunately, you have to get used to that. And beta will be alpha. And I'm going to say true. And I get the same exact probability back. If we expanded that a little bit more and expanded the verification, again, I'm getting the same exact probability back. That tells me that my equation here is 100% correct. As a matter of fact, I wrote to Excel developer to add this formula, but I guess they only consider ideas that have high votes. If we go back here, this is the link. You can go to any browser and type bit.ly/inverse for Weibull, all lowercase. And that will take you to an Excel developer form where anyone can add a suggestion. And I'm basically stating what I just told you, and the more votes we get, the more developer can look into that and hopefully integrate it in one of the next Excel versions. So if you support that, please go ahead and vote. As you can see, I don't have a lot of votes. I did that 8 months ago, and at that time I was not TA for any class, so I did not have a lot of support, but maybe that will be a good semester for you guys to give me some support. All right, we'll go back. So now I was able to verify this one, so I don't need the verification anymore. Let's just expand my formula and get a lot of time. Now let's do exactly what we did earlier with the normal distribution. For number of sample, I'm getting 2400. I need to get the average of all of these sample times and also the standard deviation of these sampled times. Please remember here, the mean and the standard deviation of this data has nothing to do with the alpha and beta. I'm sure we all know that by now. But what if I decided to compare the mean and the standard deviation for the sampled times that I obtained and compare it to the mean and the standard deviation of the Weibull distribution? There is an excellent book called Probability Distribution Used in Reliability Engineering. And this book have a section for every distribution. So if I went to the Weibull, I can find this is the mean of the Weibull distribution and this is the variance. So if I get those two, I can get the mean and standard deviation. Let's do that. All right, the given mean will be alpha multiplied by gamma 1 plus 1 over beta. All right, so I just entered my equation for the variance and I took the square root of that, so I was able to obtain the standard deviation. And once I expand this one, now I have the mean and the standard deviation of that Weibull distribution. And we're going to do the same. We're going to take the mean of the sampled times and the standard deviation of the sampled times and see how close we're getting. So we'll start. And you see how close it's getting, right? Almost every time it's identical. Again, let's do the reverse. Let's go down to only 25 sample unit. Means that only go to 29 and 29. I'll delete those. You still hover around the mean and the standard deviation, but now you're getting a little bit off. Again, remember, we're on a really small scale, so technically, if I increase my scale from 0 to 10, and I increase it to 0.5, you see that we are hovering around it. Now you're looking at it from a larger view. And that's, again, how Monte Carlo can be simulated in Excel. Before we wrap this video, I want to show you one example from my workplace, something I worked on personally, and I was able to utilize Monte Carlo. I changed some of the tasks name for confidentiality, of course. But what I did is I have a multiple task, and I wanted to know how long it takes this task. You have to bring a sheet, you have to drill it, you have to weld it, you have to inspect it, and then you have to put it away. And this is like a manual labor. So every time it takes different time because the skill of the labor, or if he was distracted talking to someone. But I wanted to get an average, how long it takes for this particular task to happen. So what I did is I started to observe. For example, this can be new sheet. This is drilling. So I observed some operator doing some test, and I documented the time. And then I put all these times together here. So I know for a new sheet, one time it took 30 seconds, 30 seconds. One time it took 1 minute. He might have been distracted. 50 seconds, 30, 30, 50, 35, different times, right? But using this data, I can go and take the average of this data and the standard deviation, and now I was able to obtain the normal distribution that governed this particular task. Drilling sheet, I was only able to observe it 3 times. Again, the more data, the better, of course, but I only get 3, so be it. I took the mean and the standard deviation of that particular task, so I can now know what is the normal distribution that governs that. Welding sheet, that is done by a robot. It's always 11 seconds. So I just left it 11 seconds with no standard deviation. I know this task will be always 11 seconds. Inspection takes time, and it's done 2 at a time. So for 2, it took 3 minutes one time, 130, 2, 145, 150. I divided it by 2 in order to get the time needed to inspect 1. And again, I took the mean and standard deviation for that particular task. And again, for put away. Now I have one distribution for every task. How can I utilize Monte Carlo for that? Let me show you how. I did sampling. I know that the sheet requires mean of 43 seconds and standard deviation of 20, and I start to sample a lot of samples, almost 15, 55 for some reason. I sampled all of those, and then for the drilling, I have the distribution. I sampled a lot, 1,500. I can go to 2,000, 5,000, 10,000, whatever your data stabilized, and I'm going to show you in a second when to stop. For welding, this is, as I mentioned, automated, always 11 seconds, no discrepancy here. Inspection, changes, put away. So basically, I did random for each one, and then I start to add the time. I'm just adding different probabilities or possibilities together to get what is the full time that's needed to do the full task. Bring the sheet, drill it, weld it, inspect it, put it away. So I got different times, of course, right? It can fluctuate. But the beauty of Monte Carlo is, as I did that 1,500 time, now all this sum of time, I can reverse it back and take the average of that and the standard deviation of that. From all of that, I was able to obtain that the mean time for this task is 3 minutes and 42 seconds with a standard deviation of 31 seconds. So basically, I can say that this task can go from 3 minutes and 10 seconds to 4 minutes and 20 seconds, give or take. And you can see why I stopped at 1555, because as I'm hitting F9, I'm getting the same or close enough value, 343, 342, 341. So this is when I know I stopped. I don't have to go to 10,000 because 1,500 did me enough to get my mean distribution stable enough. Okay, so this was one example for when I use Monte Carlo simulation to resolve a problem in my workplace, but the sky is your limit. Now you know the tool, you can apply it as needed. This is the end of our video. I am looking forward to meeting you on Monday and Wednesday if you have any question, and enjoy the rest of your day.